So we covered some of the definitions, including a relation, and now we are ready to look at what is a function. Okay, so the proper definition of a function is going to be this. Definition: a function f from a to b, a function f from a to b is a relation between the two sets, is a relation between the two sets A and B, between the two sets A and B, that satisfies the following properties. That satisfies the following properties. Okay, first, for every A in A, there exists a B in B, B in B, such that A are B. Okay, so for every element of A, we should have some element of B that is related to A. And second, if A are B and A are C, then B is equal to C. That is to say, the image is going to be unique. Okay, and we generally use the notation. We generally use the notation f of A is equal to B to denote A R B. Okay, so you have seen functions before. You have probably done calculus, you have done some other courses, you have seen functions before. But this is the formal definition of functions that we are going to use. And this is what we are going to use to prove other things. And all our statements are going to be using this definition. So A is called the domain, A is the domain, and B is the range. Okay, so not everything in the range has to have something that is mapped to it. Those are special functions, and we are going to look at some of the special functions now. Some important definitions, some important functions. So some important functions. First, for any map, for any set A, the identity function, the map identity, generally denoted by A, is the function from A to A, which defined by f of A is equal to A for every A in A. Okay, so this function just sends everything to itself, and that is the nice map. If A is a subset of B, right? So last time I introduced the two ways of writing subset and proper subset. Here, while I am writing a subset of B, I mean just a subset, not a proper subset. I will be using the notation this is proper subset, for the simple reason that I don't want to draw an extra line every single time. Okay, so only if I need to denote proper subset will I use that notation. This notation is going to mean just any subset, whether proper or the whole set. The map, generally denoted I or iota from A to B, is the inclusion map. A to B defined by iota of A. Iota of A is equal to A is the for every A in A is the inclusion map called the identity map, and this is called the inclusion map. Okay. Third, if A is a function, if f is a function from A to B, and C is a subset of A, and C is a subset of A, then I can restrict the function. Then the function f restricted from C to B given by f restricted to C of C is equal to f of C for every C in C. For every C in C is called the restriction of f to C. Okay. Number 4. If f goes from A to B and G goes from B to C, then the composition of f and G denoted G f of A is G of f goes from A to C and is given by G O f of A is equal to G of f of A, right? And it is for every A in A. Okay. Now keep in mind, if this, GOF has f happening to A first, then G. You cannot do G first to A and then f, because G is a function from B to C, not from A to C. Okay? So these are some special kinds of functions. And now we are going to look at certain definitions related to these functions. Definitions. You have seen these definitions before, hopefully. Let f be a function from A to B. First, suppose E is a subset of A. Then the image of f of E is of f under E of E under F is defined by the set f of E is defined as f of E is equal to all the f of x such that x belongs to E. Okay, note, this notation is also sometimes written as f of E such that x belongs to E. Okay, so let me just make this clear. Such that. Okay, both of these mean such that. It depends on who is writing. Oftentimes I will generally use the vertical line, but sometimes I use the double dot when it's confusing. If I'm looking at absolute values, or if I'm looking at A divides B, then these can become confusing. Okay. if f of A is equal to entire of B, like generally the image of A is going to be some subset of B. If the image of A is entire B, then we say that then say F maps onto B, or say F is surjective. Say F is surjective. Okay. Second, if G is a subset of B, if G is subset of B, then the inverse image, then the inverse image F inverse G of G under F is going to be defined as is F inverse of G is equal to all elements X such that F of X, so X in A such that F of X belongs to G. Okay, so these are all the elements whose image is in G. Okay, so this is also, the inverse image is also called a pre-image. Inverse image is also called pre-image at times. And if Y belongs to G, we define F inverse of Y is equal to all the elements X in A such that F of X is equal to Y. Okay, which is basically F inverse of the set, singleton set Y. Okay, if F inverse of Y contains at most one element, for every Y, then we say the function is injective. Then say F is injective, or 1 to 1. Okay, 1 to 1 is often denoted shorthand by 1 1. Okay, and if a function is both 1 to 1 and onto, if F is both 1 1 and onto, then F is surjective. Then F is bijective. Okay, so 1 1 is injective, onto is surjective, and in that case F is bijective. Okay, so now I am going to write down some properties related to functions that are true. I am not going to prove these. You should try to prove these on your own. Okay, so since this is supposed to be a refresher, I am going to hope you have seen these before. If you have not, try to work through them. If you are unable to, I can maybe direct you to the proper place, or if you're unable to understand something, I can explain it to you. But I generally want you to do these by yourself. Okay, so exercise 1, show show the following statements. Show the following statements. These are not strict homework problems because this is something you should technically know from before and you should be able to do it. But if F and G are both injective, then so is F composed G, or G composed F, whatever. Okay, let me go G composed F because that is the one I've used before. G composed F. I'm going to say F from A to B, G from B to C. Okay. Second, if F and G are both surjective, then so is G composed F. Third, if G composed F is surjective, then actually so is G. So we are not claiming that F is surjective or not, and which is the fourth point. Surjectivity of G composed F. G composed F does not imply F is surjective. So I'll generally just write SURJINJ for injective or injective. If G of F is injective, then so is F. And sixth, injectivity of GOF does not imply injectivity of G. Okay, I'll give you a hint for problems 4 and 6. If you're looking for bijective functions, you will not find counterexamples. You won't find counterexamples which satisfy 4 and 6, and because the way bijective functions work, you won't find any counterexamples in those. Okay, they are always injective as well as surjective. So you want to create examples where one of them is not injective, they are not surjective, so that you can play with them. Okay, proposition. For any collections, let F. So now I'm going to take F from X to Y rather than A to B, because I'm going to be looking at sets, a lot of subsets. For any collection of sets A of X, first, F of union A belongs to A is equal to union A belongs to A, F of A. Okay, the union works out perfectly nicely, but second, f of intersection of A in A of A is only contained in A in A. Okay, it need not be always equal. Okay, only one-sided inclusion is true. Generally, there are very specific cases when it is true, and that is f is injective if and only if and only if, which from further onwards I'll be denoting IFF, if and only if for every collection A of X we have f of intersection A in A of A is equal to intersection A in A f of A. Okay, so clearly if they're injective functions, it works. Otherwise, it does not work. If B is a collection, let me go with fancy B. If B is a collection of subsets of Y, then things are slightly better. F inverse of union B is a subset of my fancy B. B is equal to union of B in my fancy B, F inverse of B, and F inverse of intersection B belongs to fancy B. B is equal to intersection B belongs to fancy B, F inverse of B. Okay, so both of these work nicely. I am not going to prove any of these. I am going to assume that this is true and you should be able to prove these. Okay, I'm going to stop this review right here. These are the things that we'll need for now before we move into we get back to real and complex numbers. Okay, try to prove these. Let me just write it out. Proof left as exercise. Left as exercise. Okay. If you have seen these before, great. Lot of books and everything have these proofs, so they're not really hard. Also, I hope you know how to write a proof so that you can write these properly. Okay, but it's mostly just chasing an element. Take one element of one set, show it belongs to the other. Take an element of the other set, show it belongs to the first. That is how you show equality. Okay.